We're going to go ahead and look at the next type of models, which are ensembles. Within ensembles, we're going to look at bagging as our first um, ensemble model to look at. Remember the bagging. In bagging, we produce an ensemble that is a combination of different trees that are obtained using bootstrap sampling on the data. For this example, we're going to call this model 6 to just keep with the same structure that we had before. In this model will be an ensemble of, again, back an ensemble of 100 trees. I have already loaded the vet training and the vet validation dataset. And just to remind you of the structure of the data, we're trying to predict the target B variable, which is whether a donor has donated after not after being inactive for some time. So we have the options of no and yes. So this is a binary response. So we're gonna use the package IPRED for the bagging ensemble, and we are gonna use the package PROC for ROC and ROC curves and AUC values. Let's use the R part the, just to create the trees using recursive partitioning. So let's start with model 6 and use the bagging function within the IPRED package. So we're going to use target B as our variable of interest, and the data is just the vet training. Within the IPRED function, the bagging function, we need to say how many trees we want to combine, and that is 100. We can use some control on the trees using R part control, and we can set the CP value to something different than this, knowing that the lower the CP, the larger, the deeper the trees. We can use also cross-validation different than 10, and finally we can use the out-of-bag estimate of the misclassification error. While this is running, we can talk about the fact that an ensemble basically takes time to run, because on the background we are basically creating 100 trees using the control, the stopping criteria that we want to use. If you see that this is taking too long, we can set the options differently, such as different number of trees, a higher CP value to just limit the tree to stop the tree from growing larger. We can set also the maximum depth to be something different. So having run that, we can take a look at model 6, and we can see that the misclassification error estimate is 43%, 43.55. Something else that you can also do with a bagging ensemble is to look at the summary, just as you did when you had a logistic regression model, and that basically shows or spits the whole output, including the trees up to all of the trees, and the information about how was each tree obtained. So let's take a look at an example, model 6. We can look at model 6, and then within that we see that we have object and trees. So let's take a look at the first tree. So we can do that by using double brackets and then the number of the tree that you want to look at. So the first thing that we have here is the observations that were chosen in the bagging sampling. So you can see the different observation numbers that were chosen. Again, in total 6,780 observations, which is what the original training data set has. And this is actually the tree that was obtained in that particular sample. So this is tree number 1. You can always do r-part plot on that particular tree. So let's do that. So let's do r-part dot plot of that particular tree. So we want to use the $b tree because that's the name of the object for this particular package. So we can see that this tree uses the gift average, the average of the gifts, the demographic cluster, and you can see that the demographic cluster is one of the most important variables in this tree. You can do the same thing with other trees just for fun. We can take a look at tree number 2 and how different it is to tree number 1. Let's say tree number 2 actually uses also demographic cluster and the gift counts or gift amounts. So we can see how different each tree is. Now, the ensemble is a combination of the trees, so that means is that the ensemble has to these propensities are averaged across all of these trees. So that's why a bagging ensemble is a black box, because although we can see what those trees are individually, when they are put together, we no longer have something like a rule that we can explain what that tree is. So having said that, let's go ahead and do the predictions. So we're going to use, we're going to just get the propensities for both training and validation. So let's, to keep the convention, let's use p6.train for the propensities of the training dataset, and we'll use the predict function. And so we will use we need the model 6 here, and data is equal to vet training. We use the type to equal to prop. And finally, we want to select the second option, which is the propensities that the donor donates again. So the option number 1 is no, option number 2 is yes. So that's the reason why we use that. We're going to use the validation propensities, just do the same thing, valid, and the only thing we need to change is change this to new data. And that's basically how we get the propensities for the validation. Let's get now the ROC curves or AUC values for both training and validation. And we can do that. Let's name these R6.train. We can use the ROC curve. And we need, first of all, the actual value and then the propensities to get that ROC curves. So let's just can use the plot R6 train to just basically plot that ROC curve for the training data. So then we can see that it does better than random. And the actual AUC value for this is 59.67%. Same thing for the validation data set. We can do P6 valid and RC valid here, and let's name this R6 valid. So we can take a look at how different is the validation AUC compared to the training. And in this case, we have a validation ROC AUC value of 58.63%. So having said that, that is an indication of how the model is doing on both the training and the validation in terms of the AUC values. We see that the model's doing better than random, and compared to the other models, those are the values that we want to keep. We want to keep statistics such as the AUC. We want to know something about the complexity of the model. So in terms of complexity, we can think of when we're doing samples of, well, how many trees are we trying to combine? In this case, it's 100 trees.